Unit 4. Okay, we're going to start with 4.1. It's extreme values of functions. Extreme values. When I say extreme, what are we thinking? Anyone have any ideas? What? Yes and no. Could be. I guess we'll have to see. Extreme. All right? The absolutes. Or sometimes they call them global extreme values. Local, those are really mins, maxes. Mins and maxes, extreme, extrema. And why are we going to do this? Because finding the maximum and minimum values of a function is called optimization. It's like maximizing something, like money, doing a business. Okay? Space, that you're building. I said like space in outer space because can't maximize outer space, it goes on forever. But technically nothing will occur. There's got to be an end. We're just nothing happens. I don't think. Or it just goes on forever, but things can't go on. We're just so small that it seems like it goes on forever, but eventually it should happen. But it's too small to realize it. Yeah, right? Basically, good talk. All right, so there we go. And it's important for real world problems. This is where calculus really comes into play for real world problems with maximization. So, the mileage of a certain car can be approximated by this function here. Mileage with respect to v, which means velocity, okay, equals 0.0015 v cubed minus 0.032 v squared plus 1.8 v plus 1.7. What speed should you drive the car to obtain the best gas mileage? Now that is kind of a ridiculous problem. This equation probably wouldn't be used to model any sort of car that's actually moving, but we're just doing it here for calculus purposes. All right, so if I were to graph this, and we can solve it graphically. We know how to find mins and maxes graphically, don't we? I'm going to take this problem and I put it in a calculator. You guys want to go ahead and put it in a calculator too. And I made my window the following. My x value went from 0 to 100. And my y value went from 0 to 60, and I went by 20s. That gives you a nice idea of how the graph actually flows. And at that point, once we have that picture, we can find our optimization, which means we can maximize our miles per gallon by using our calculator. I'll go ahead and give you guys a minute to do that. So I went ahead and I put this in my calculator. And here's the equation. I typed it all in. And my window, again, I made it from 0 to 100 on the x. I went by 20s. And then from the y min and max, I will go from 0 to 60. And again, the scale by 20s. And when I graph it, well, I should do the same thing for the notes because I pulled that problem from the notes. Now, if I want to find the best mileage, let's not forget, our mileage is our y. And our variable v, which is, I guess, our speed, velocity, is the x-axis. I want to find, what does it say in our notes? When you drive what, your gas mileage is what? All right, well, how do we find that? It's probably at this point right here, our max point. That maximizes, that optimizes our situation. And how do I find the max point in the calculator? Seconds trace, because I want to calculate my maximum. And we're going to bow tie, which means I got to be to the left of it, hit enter, then be to the right of it, hit enter, and hit enter one more time, and that will give us our values. So let's go over here. The left of it, hit enter. To the right of it, enter. And the arrowheads should point to each other. It should look like a bow tie, and it does. And hit enter one more time. And bam. So, this point, when I drive, which is, what do you think is going here? My x or my y? Well, mileage is our y. This is our y. So this would be your x. Okay? When I go, excuse me, I'm looking for my x. My x is down here, my bag. X, 38.6, let's call it. My gas mileage. Calculator doesn't for me. But in all the instances that we do, sometimes the calculator can help you, and sometimes it's not going to help you. So here we go. The absolute extreme values are either the maximum or minimum points of the curve. For example, with the car, it happened to be the max point. It was a high point. All right? They are sometimes called global extremes. It's rare that you hear that, but every once in a while you hear it. They are also sometimes called absolute extrema. Okay? Absolute extrema. So those are some terms. Whenever you hear them, you should be thinking mins and maxes. All right? By the way, extrema is the plural of the Latin word extremum. Just in case some of you guys are interested in kind of legal side of okay. All right. So, extreme values. Okay? Extreme values can be in the interior or endpoints of a function. If the function goes on forever, no. But if it has endpoints, that endpoint, if it's the highest point on the graph, is considered a maximum. If the endpoint is the lowest point on the graph of the function, then it's considered a minimum. So, for example, this top left graph here, do you think it has a maximum? There is no absolute. You're right, there is none. How come? This arrow has to go up. It doesn't stop. All right? Do you think it has a minimum? It does. It does have an absolute minimum. It's right here. Remember, visually, a maximum needs to go up and come back down. It has to be a peak of a mountain. This is what a maximum has to be. A minimum has to be like that. Unless it's an endpoint. If I have something like this max here, goes up, comes down, and comes up like this will be the actually highest point. It stops. If there's an arrow height, then it will. Okay? So let's take a look at the top right here. Think it's a maximum? Yes. Yes, because it's an endpoint there. It stops right there. It's the highest point. You think there's a minimum here? Yes, this is an endpoint. Bam. It has an absolute max and min. Well, down here, bottom left, what do you think? Do you think there's an absolute minimum or maximum?
There's a max. There's no min.
So there's a max, but there's no min. And you'd be correct. How come?
There's a hole.
There is a hole. It will get closer and closer and closer and closer forever to that hole without touching it. So, what about this last one? Bottom right. No and no. No and no. Okay, in the bucket. Okay, extreme value theorem states, all right? And a lot of stuff is okay to understand this way when you start putting it together, but you should be able to perform it. All right? So that's the doing part. If f is continuous over a closed interval, meaning, let's take a look at this first squiggly line here. The closed interval will be from here to here. And if it's continuous, so closed interval, those are the two dots I just put here, right? There's the interval. We'll call this, I don't know where this is, point A on the graph. Here's the x-axis. Okay, here's B. The interval will be from A to B. It's closed. All right? What does continuous mean? Thank you. Thank you. Thank you. I can draw this function without picking up my pencil at all. It is continuous. It never stops from point A to B, which is our interval. Our interval will be from A to B. Okay? Then f has to have a maximum and minimum over that interval. Remember, it's closed. It doesn't go on forever. If it goes on forever, there's no max, right? It goes up forever. But an endpoint can be a max. So if it has endpoints, okay, well, it could have a max in it. And if it's continuous, so it starts somewhere clearly, and it stops somewhere clearly. Without looking at your pencil, there has to be a point where it's the highest point. There has to be a point where it's the lowest point. So right here, high points, low points. Okay? This first example is a great example of having a max and minimum inside the endpoints. Okay? When it's interior, it means it's not at the endpoints. Obviously, there are endpoints and there are interior points. The endpoints, I think, are pretty self-explanatory. Those are the points at the end. And everything else between them are considered interior points. These have to fall inside of the endpoints, okay? No, go ahead. Let me explain.
Interior points is further, right?
No, the interior points of this graph. Remember, a line is made up of an infinite number of points. It starts here. Point. You know what I mean? They're all coordinates, aren't they? And they're all so close together that it's like a straight line. So here's where it ends. Here's where it stops. Here's an endpoint. We call it EP. Here's an endpoint. All these other points are in between. They're inside. They're considered the interior points. So it's telling you the maximum and minimum have to be in interior points. Here is a minimum. Here's a maximum. They have to be interior points. It's just an example. All right? Now this middle one, the max and min have to be at the endpoints. How come? Here's an endpoint. Oh, that also happens to be the maximum point. That's the highest point there. Here's an endpoint. Oh, look at that. That happens to be the lowest point. That's the minimum. All right? So it's just telling you, the min and max, sometimes it's not the endpoints. Sometimes it's both of the endpoints of the min and max. And sometimes, well, maybe one of the endpoints is the min and max, and one of the interior points is the min and max. Like right here. This is definitely the minimum. This is definitely the maximum. This is an interior point for the maximum. This is an endpoint for the minimum. So, I mean, it's not like, oh, it has endpoints, it's got to be the endpoints. No. Whatever coordinate is the tallest. The highest up is the max. Okay? And same thing for the minimum. All right, the critical points. And this is where our knowledge of derivatives and slopes and min and max points, even from pre-calc, are going to come crashing together. All right? Critical points. A point in the domain of the function f, at which f prime, what does f prime represent? The derivative, which is also the slope. Good, no, good, this is good. You should be programmed to know that if you see the derivative, it also means slope. Okay? So it's on a function where the slope, which is the same as derivative, is 0. If the slope is 0, what type of tangent line is that? It's a horizontal tangent line. Okay? That means horizontal tangent line. Okay? So the slope is either 0 or does not exist. That's considered a critical point. Meaning, I draw a parabola. That's a parabola, right? Where is the tangent line 0? At the top, right here. Where the tangent line is 0, that's called a critical point. Okay? That's a critical point. And the maximum and minimum points in the interior, not the endpoints, but in the interior of a function always occur at critical points. But critical points are not always the maximum or minimum. Weird. So, my max and min are always critical points. So if this is a max, let me do this. Okay? For the sake of argument. Don't start lower than the rest. This is a max point. Oh, look at that. Horizontal tangent line. Critical point. This is a midpoint. Oh, look at that. Horizontal line. Yeah. Okay. Well, you would have been right. That would have been great. But critical points are not always the min and max. If I go like this, come down like this, go up like this. Endpoint, endpoint. This is a critical point, isn't it? This is a critical point, isn't it? Are they the mins and maxes? No. This is the max. This is the min. Right. Right. Okay? So it doesn't always have to be vice versa. But if you have a horizontal tangent line, if the derivative is equal to 0, then I take the derivative of something equal to 0, that might be one of your mins and maxes. Okay? Finding maximums and minimums analytically. Here we go, ready? These are the steps. These are the steps that we're going to take, and they're going to be easy, and you're going to see that they kind of resemble things we've done in pre-calc. Find the derivative of the function, because the derivative also means the slope, okay? And we're going to determine where the derivative is 0, because when the slope is 0, it has the horizontal tangent line, right? And if it has a horizontal tangent line and the slope is 0, we know that's where a critical point happens. Okay? So we take the derivative of a function, set it equal to 0, okay. And we find that, right? Because the step 2 tells us. We're going to actually find the values of the function at each critical point. So that means solve. We take our derivative, we determine where the derivative is 0 or undefined. Okay? And once we have those, we find the value of the function. So here, we're going to find the x's, which will give us a 0. Alright? And then, well, we got to find the y's, don't we? X's and y's. Right? Find the values of slopes for points between the critical points. Alright? The easiest way I can tell you to tie all this together is number line. Remember when we graphed a couple things without a calculator? We had to find the derivative for the slope and all that jazz way back in the day. We have f of x, right? Well, we're going to find out where f of x is equal to 0. We find where f of x is equal to 0. Okay? I don't know, maybe here and here. It's 0 here and it's 0 here. This is my f of x, is my slope, right? Now what it's saying for step 3 is find the values or the slopes for the points between these. So I take this value here, let's call it c, and I put it in my derivative and find out if it's positive or negative. It might be positive here, it might be negative here, it might be negative here. What does that tell you? If I have my derivative is negative, what does that mean? That the what is also negative? The slope, which means wouldn't it go down like this? If the slope is positive, wouldn't it go up like this? If the slope is negative, wouldn't it go back down like this? So chances are, my max point is probably here, where the two slopes converge up. My midpoint is probably here, where the slopes converge down. You see what I'm saying? You can almost see the graph start to unfold. It kind of goes down, comes up, and goes down. So it makes sense that this will be a max point, this will be a midpoint, wouldn't it? So once you find your zeros for your derivative, you just find a value in between. It's positive, slopes up. It's a negative, it slopes down. What's the last thing we need to do? Yeah, which means, okay, this is nice. Let's say it went like this. Up, down like this, and down like this. This is still a max and min, but they're not the highest and lowest points, are they? The end point is technically higher than this is. This end point here is technically lower than this. So after you figure out the y values for here, it tells you how high that is. You find the y values as how low this is. Check the y values for your endpoints, because maybe they're higher or lower. Always check your endpoints. Well, if you do, then you're still going to have to figure these out. If you get the endpoints first, that's fine. But then you're going to have to still figure out those if they're higher or lower than the endpoint. Because remember those three examples? Sometimes the min and max are the endpoints. Sometimes they're not. Sometimes they're both interior points. And sometimes one's an endpoint and one's an interior. So this last step of just checking your endpoint is just your last thing to make sure, okay, I got my information. Oh, let me make sure the endpoint isn't higher or lower. Okay? Find the absolute maximum minimum values of this function, f of x equals x to the 2/3, on the interval from -2 to 3. So right off the bat, I know when I find this, and I find my min and max and my slope, so if it goes up or down, I find my 0 point, or it goes up, I'm ultimately going to have to test these two endpoints to see if they're higher or lower than everything else. Okay? So, what's the first thing we need to do? We can. But what's going to go on that number line? No, you're right. We're going to get the number line, but it's going to represent the what? Yeah, the derivative.
I thought you meant like -2 and 3.
Oh, on the number line.
Yeah.
Yes, yeah, that you would want to probably include those would be a better picture, yes. But ultimately, it's our derivative. It's our slope that's going to tell us, okay, where it's going up, where it's going down. When it's 0, it's going to be a horizontal tangent line. So I'm going to first, when I take the derivative of this, and I'm going to use just my normal exponent rule. What do I do? I know. What do I do? Yeah, the exponent comes down. If that was x squared, wouldn't it be 2x, right? So I take my 2/3 down here, times x, and then I do what to my exponent? I subtract 1. So what is 2/3 minus 1? It's -1/3. Okay? Now, that's my derivative. I find where that is equal to 0. That's going to be my starting point. And there's only one spot.
Okay.
Wait. I find where it's equal to 0, and let me finish and answer your question. I want to find where it's equal to 0. How come? So the slope is 0, that's where the horizontal tangent line is, right? That's probably where a min or max might be, unless it's at an endpoint. Okay? So, I take my derivative and set it equal to 0. What is the only value of x that's going to make that 0? 0. 0. So, x equals 0. That's where there's a critical point. That's where my derivative is 0. That's where there's a horizontal tangent line. So now, on my number line, I now know that I have a 0 at x equals 0, right? That's my 0 derivative. We can go, like Zach says, let's put the endpoints here. We're going from -2 to 3, right? These are my endpoints. This isn't actually the axis. I'm not graphing it. This is just going to explain to me the derivative, how the slopes work. Now, if I know it's a horizontal tangent line here, well, I want to know if it's going to be sloping up or down on the left and right of that critical point. You see what I'm saying? And how do I do that? I don't know. Let's pick a number and check it. Let's pick a number here. Let's make it easy. Let's take -1. So I can pick. I always use 1s and 0s if I can. They're so much easier. Okay? So if I pick -1, okay, and you can use your calculator, that's fine. I have no problem with it at all. Okay? I have no problem with it at all. And I'm going to put into my derivative f prime of -1. That's 2/3 times -1 to the -1/3. When you hit equal in your calculator, what do you get? The cube root of 1 is 1. That'll say negative. It's going to be -2/3. Is it? -2/3? So this is actually -2/3, which means between my endpoint and 0, this is going to be a negative slope. Okay? What about if I pick +1? Okay, now I'm going to try f prime of 1. Well, that's 2/3 times 1 to the -1/3. What is that going to give you? It's going to give you 2/3. It's a positive value, right? So guess what my graph is going to do here? It's going to slope down, flatten out here, curve, because that's where the horizontal tangent line is, right? And it's going to slope up. Yeah, hold on. So, how do I know? If I need the max and the min, don't I need the y value? How high and low it goes? So how do I figure out what the y value, if these are my x values, how do I know what the y value is when x is 0? I plug it into my original function, don't I? Y is the same thing as f of x. So if I want to know what y is, when x is 0, I plug in a 0 there, don't I? So that would be 0 to the 2/3, which is 0. So guess what? When x is 0, y is 0. So this is going to happen at 0, 0. I tell you what, that looks like a midpoint. I just got to determine which is going to be the max point, at -2 or at 3. Because you see the way that graph works? Nothing can be lower than that. So that's going to be my midpoint. Now what about my max point? I've got to try -2 and 3. So someone tell me, what's f of -2? That's -2 to the 2/3. What do you get there? -1.59?
Yeah.
I don't know. And -2 is -1.59. That's my y you're telling me, huh? That looks like it's below 0. It's interesting, isn't it? Did we mess up here?
No.
That's still negative, right? -2/3? At 0, it's 0. So this is a negative, something comes up. We'll have to graph it after WC. Does that look like though it doesn't make sense, Stephen?
So I'm going to go ahead and that.
I don't know. Let's see. Let's see. We're going to end up graphing it later, absolutely. So what about f of 3? I want to find f of 3. That is 3 to the 2/3. What do we got there? 3, comma, that's my x value. What's my y? Who's got that? What do we got? Come on. 2.08, is that right? You got 2? Wait a second. Wait a second. 3 to the 2/3, I think that's 2.08. I don't think it goes in either. So this will be at the point 3, 2.08. And we're saying this is going to be at -2, what? Which looks like it's the lowest. This one right here. Now look at the way our graph is. Now remember, that's nice. Now remember, it's that at critical points, they're not always min and max values, right? But if it started below here, wouldn't it be coming up?
I didn't know.
Maybe we did it wrong. Let's see. It's interesting. Second plus 7, 1, 2, enter. I am going to graph y equals, and it is x to what? The 2/3?
Yeah.
So I'll do an exponent, alpha y equals, enter, 2/3. I'm going to graph it from -2 to 3, because that's my interval, right? So from -2 to 3, go by ones, and then we'll go, I don't know why, because be from -10 to 10 is good. Let's graph that. The coordinate here should have been positive at -2. That's where the mistake was made in the calculator. So let's take a look at this. Did you put the -2 into the derivative formula, or did you put it into the original function?
Original.
So if we have -2, yeah, where's my 2? -2, parenthesis, and we're going to put it to the what? 2/3. You guys know, how come you think that should be positive? Because I'm going to square something and take the cube root of it. If I square even a negative number, should it be positive?
Yes.
It's a positive 158. It's a positive 158. So this is actually positive 158. This was positive, and that's what we checked. Our minutes here and our max, 2.08 is definitely taller. That's our max. Our math was right. Our calculator work was wrong. Our analytical stuff was right. All right.